Normally, when we decompose things, they decompose by like heat, or exposure to certain other reactants. In this case, we aren't exposing it to, let's say, oxygen or water or other things that might decompose it. And so there are a couple of strategies. One is we can just guess, and we can continue guessing until we figure out kind of what um, we can expect. Let me make sure this is correct. And it's not showing up. Oh, there it is. So when we guess, though, we want to make sure that we're guessing things that seem reasonable. Like, for example, some people will guess things like potassium plus Cl plus O. Atomic chlorine and atomic oxygen aren't reasonable because those are quite unstable at room temperature. Some people might guess ozone. Well, ozone is quite reactive. It's not very stable, and so they might say, okay, it's going to be plus chlorine plus ozone, but these ones aren't going to be nearly as favorable as this one here, because this one is more what we would expect. Now, as far as reactivity goes, let's take a look at this. So when we look at the reactivity, this is just potassium ion, this is a +1, and we think of potassium ion as far as chemical properties go. Does it have much? I mean, it's metathesis. Would you expect much for potassium ion? Nothing. Group 1 are soluble. It's not going to form a gas. It's not an acid, so it's pretty unreactive. That's why, people can eat potassium, and it's generally regarded as safe. There are lots of potassium salt, but against sea salt, which we don't worry about. Now, chlorine, the reactivity of chlorine is going to depend on its oxidation state, its charge. So, for example, if the chlorine is -1, that's totally unreactive. People sprinkle that on their French fries without, dying, as in sodium chloride. But what is the oxidation state of chlorine here? Well, first we do potassium, and then we do what? Oxygen, -2, and then we do chlorine. And chlorine is going to be what? +5. According to the rules in chapter 3, I think it was. So, if looking at these three, which one would you suspect is the most reactive out of these three? Yeah, easily. This is going to be the most. And as far as reactivity goes, we need to know, is it the most reactive acid, base, precipitating agent? And what is it? Metathesis? Now, these aren't free ions here. We're looking at the ClO3- ion. And so this is a polyatomic ion and the potassium ion here. It's not free, but it's going to be the most reactive element or atom in this compound. And it's the most reactive because it should be a good what? It should be a good oxidizer. And so one way is we just guess. Another way is to look at the potential reactions. When something decomposes, we place it under heat. It's heated. Delta is a symbol for heat. So when things get hot, there are reactions that normally wouldn't occur, but do occur. And so one of the reactions here is chlorine wants what? Chlorine wants electrons. Can it take it from potassium? No. Oxygen is quite happy at -2. It's very stable. And I don't expect chlorine to strip electrons off oxygen. But when you start to heat things up, then you have to watch out. If you're dealing with, let's say, an explosive compound, you don't want to heat it up. Usually you want to keep it cold. You want to keep it cold so that unwanted reactions don't happen, right? It doesn't explode. And so the same thing here. I don't want to heat up chlorate salts. I don't want to heat up any kind of salt like this because unexpected reactions can happen. And so one of the things is it's not going to take electrons from potassium, but if you get it hot enough, what could happen? It could take electrons from oxygen. So if oxygen gets stripped of electrons, we have two choices. One, it could go to peroxide, which is a -1, or it could go to oxygen, which is a 0. It could go positive, but if positive oxygen would be terribly unhappy. And so I'd say it goes to 0. If oxygen goes to the 0 state, let's say it loses electron, then we form O2. So I'm suspecting O2 would be it. Now, how many electrons, if chlorine could have its way, how many electrons would chlorine take in total?
6.
Yeah, it takes 6 because it wants to form chloride. And then potassium is just going to stay as is. So what we suspect is we're going to form potassium chloride and oxygen gas. And so I think the products will be potassium chloride and oxygen. And to balance this, we'll need to make this at 3 halves on the oxygen. And potassium chloride is a stable salt. I mean, people eat this stuff in some more exotic salts. So that's another approach. The other approach is to just kind of break it down in terms of reactivity, and then see what's possible.
Are there any steps you would need to show for that?
No, it's fine if you just guess. Come up with some guess. The other thing is sometimes it's hard to predict, so that's why we have skeleton redox. In skeleton redox, would go.
Yeah, that was kind of my first idea to try skeleton, but we really have
Well, skeleton, you have to have some kind of product in there. We don't have any product, and so we know the driving force is we want to go from less stable reactants to more stable products. So if you can figure out what the most stable combination of products would be, like KCl and oxygen's no problem. We got 20% oxygen in this room. We got potassium chloride salts. We don't expect any reaction. That's a pretty stable combination. And so that kind of stuff we can look at as well. And so this one is a little bit different. This one is not a chart method. And so and for redox can get a lot more complicated. And so there are other things that we can look at in terms of redox. So we learned certain patterns like combustion reactions. In combustion reactions, what do we form? And so I didn't put any hard combustion reactions here. But I could have, and it's going to result in the same type of analysis that we do for KCl3. So for example, let's say I had a CXHYSZ compound, and I combust it. Well, I know the CO2 is going to be completely combusted to what? I mean, C will be completely combusted to CO2. And so how did we figure that out? We just figure out that if there's enough oxygen, we're just going to completely oxidize it. Then the hydrogen H plus is, I don't know what we're going to do with the H plus. Normally H plus will go to water if there's plenty of oxygen. But what about the sulfur? And so this is the same scenario as we had up here. What do we form with the sulfur? Now, I don't want to come up with some ridiculous ones. Maybe we just form elemental sulfur. That's possible. But if you're burning it, does sulfur burn? Yeah. If sulfur burns, then what do you expect to form?
Sulfur dioxide.
Maybe sulfur dioxide. It could form sulfur monoxide. It might form sulfur dioxide. How about sulfur trioxide? It depends on the oxidizing conditions. You might have seen in the book, back in chapter 3, it's sulfur dioxide that forms. But why sulfur dioxide? Because sulfur dioxide is sulfur in the +4 oxidation state, whereas sulfur trioxide is sulfur in the +6 oxidation state. So if we're going to completely combust it, why don't we all go all the way to +6? And it turns out that under these conditions, maybe it doesn't quite. You need a little bit more extreme conditions, or it actually does. Eventually it goes to here. So it might initially form sulfur dioxide, which then gets further oxidized to sulfur trioxide. But there's a bit of a guessing game here. You know. The same thing here. Why did we form CO2? Couldn't it have formed carbon monoxide? Yes, it could have formed carbon monoxide, and maybe lots of carbon monoxide formed. So there's a bit of a guessing game, but we're just going to assume complete oxidation. Well, if we assume complete oxidation, then maybe we should have taken it to sulfur trioxide. But whether you do sulfur dioxide or sulfur trioxide, those are reasonable, or sulfur. These are all reasonable. Like carbon monoxide versus CO2, it's reasonable to expect maybe carbon monoxide conditions. So we assume excess O2 and then take it probably to sulfur dioxide. And getting that extra step to sulfur trioxide might be hard. In this case, it's not terribly hard. Sulfur +6 is okay. It's hard for chlorine. What's the max on chlorine? So chlorates are stable. I mean, well, not terribly stable, as you see decomposed up here, but chlorates are known. This used to be thought of as max. Most 8 salts, ATE, are kind of the max oxidized. But this wasn't the max. This turned out to be only in +5. And so they named this chlorate, but unfortunately it wasn't the max. And so they had to add one more, the perchlorate. Because this one is hard to get. And so it's not hard to get chlorate. And so if we oxidize chlorine, we can get chlorate, but it's much, much more difficult to get the perchlorate. And so this is where people thought it maxed out. And so this is why the nomenclature system is a little bit inconsistent, because most of it, like nitrate's maxed out, nitrite's not. And so that pattern doesn't hold. And so there is some guessing to the redox, because the conditions can impact what you form, And the conditions, there are a lot of variables in the conditions: temperature, pressure, et cetera, et cetera. And so what a lot of people do is they just play with adjusting those parameters and then see what they get. And to expedite this, if you just make one little adjustment, see what you get, one little adjustment, see what you get, it's going to be very time consuming. And so that's running it like in series. You do one reaction followed by the next reaction followed by the next reaction. Nowadays, what they do is they do parallel reactions. That is, they have a reactor, with like 1,000, where they can test them. Let's say 1,000 different formulations. So
would the driving force for the potassium chlorate be a strong oxidizer to weak, with weak being the oxygen?
Weaker, stronger to weaker, right? That would be the driving force. Stronger would be the chlorate ion, and weaker would be O2. Well, anyway, what is that? Were there any other questions?
What day is the test next week?
I'm thinking it's probably going to be on Thursday.
And which homeworks are going to be due? It's going to be the reactions.
Reactions and nomenclature.
Should chapter 24 add into it?
The first part. There aren't that many questions for chapter 24. And if you don't have the solutions manual, I recommend getting the solutions manual. So we finished 2 of the problems here. So you only have 8 more left to do. So the way the homework is going to be graded is you have to attempt all 10 questions. I don't check if the answer is correct. You should just check these yourself. And so this is why I recommend getting the solutions manual. That way you can check your answers. However, there are some errors in the solutions manual. Oh, this didn't format quite right. This is from an Excel spreadsheet. So I think you can figure it out.
At the very, on like the next page, is like a random graph of 28 or something.
Sorry.
Is that like,
That was a mistake.
okay. Just want to make sure I wasn't like an extra chapter.
No.
Chapter 25 is the last. So if you printed
This out and wasted 3 pages. Sorry about that. It's supposed to be on 1 page. I'll fix this. So turn in chapter 24, part 1, and chemical reactions. In theory, everybody should get 100% on homework. In practice, only a very small percentage of the class gets 100% on the homework. I think people just run out of time. But if you run out of time for the homework, then it's, I think, what you need in Chem 1B is a lot of time to study, for success. Isaac?
my question is, you probably already know this, what date
The homework is going to just be due on the day of the test. So, and it's only going to be the homework problems that are relevant to that one test. I want to see how much homework you did before the test, and so this is why I collect it. I like to collect it before the test, right before the test. I mean, you can do it last minute. That's okay.
It's not recommended last minute.
It's not recommended last minute. What's recommended is this is the way I did it, and I've evolved how I study. I usually do things last minute, everything, study, procrastinate, but I had to change that because the exams were nothing like the homework. The exams were like a step above the homework, and so if a homework problem came on the test, then I thought, oh boy, I got lucky because, a homework problem, which is easier because I've seen it before, came on the test, then I was very happy. And so what I did to prepare for those tests is I tried to do the homework as soon as possible. I didn't actually do the homework, like literally do. Like a lot of instructors say, when you do the homework, you should do it, without any aid. That is, don't look at the solutions manual. You should do it all on your own. But what I was finding is I was spending way too much time. Like I'd get stuck on a problem and I'd spend like 2 hours on a single problem, and then I have so many more left, and then I figure I'm not going to make it. And so I gave up doing that. What I did was I looked at the homework, see if I could figure it out. If I could figure it out, I'd figure it out. But I wouldn't spend much time like researching how to do it or this, because typically the exams weren't like the homework. So what I did was I just looked at the homework solutions. When I was at UCLA, most instructors there gave the complete solutions manual. So you can buy the total. Here, when I was at Santa Barbara City, none of the instructors gave the complete. They only gave the partial, and then the questions they assigned were the ones without the solutions, of course. And so to speed things up, I would read the question, think about how I'd approach it, and then see how did the solutions guide approach it, and then I'd compare. Did I do it the same way, or maybe I had no idea. If I had no idea, then at least I saw how they did it. And so the key thing was I do that, and then I do another run through. Like before the test, I'd have time to go through the homework again, and then I make little notes. What the key takeaway, like tools or methods that they did, and how it changed, either mentally or I'd write it down. And so I'd annotate my homework. And so it's not just, a lot of people will, and you can get 100% with just copying it down. You don't even have to think about it, and then some people do that. And so I was thinking, there are people who get 100% on the homework but do very poorly on the tests, and maybe that's not fair because they're going to have a difficult time in the future. So one of the recommendations that a lot of instructors make is that it should be 100% test. That's how it was at UCLA. It was 100% test. You had a midterm that's typically worth X percent in a final. Some people, they weight it equal, 50-50, and it wasn't comprehensive final. Others was like, 25-75 or something like that. One midterm and one final. But anyway, the homework, even if you copy it down, you can. But if you copy it down, I figure at least you've seen it once before, maybe, and then something might have registered.
Would you say, is your test like the homework?
Yes. Yeah. I've ever seen. It didn't start off that way. When I first started, I taught at different schools too. When I first started, boy, a lot of students complained about my tests. My tests were nothing like the homework, but I was kind of used to it. It's nothing like the homework because you're supposed to trick the students, You're supposed to trick. That was the mentality. I was supposed to trick the students, to see if they could figure it out, that kind of thing. That was kind of like the mentality at certain places, But I figured, what's the point of doing that? At least if you have the basics down, it's better. And so I try to make it not so different than the homework. Although some of them, might not look the same, or some of the questions might be tricky. It's not always straightforward. But the more you see this and the more you review this, then the more familiar you get. It's like the analogy for me is like chemistry is like this giant forest. I mean, there's so many different problems. Just like in a forest, there's so many different plants. And so if you go out and study the forest, you spend all your time looking at one tree, and you're probably going to get very good at that one tree, but you're missing the whole forest. It's better. My thinking is it's better to get exposed to a lot of different problems and see how those problems are solved than to focus on a few and do those very well. And so I prefer the generalist approach versus the specialist approach in general chemistry. In fact, in new subjects, because how do you get like 30 years of experience in one semester? Perhaps that's kind of what you're supposed to do in these classes. You're supposed to become kind of a subject expert in this. And so one way is, people who have experience. Well, they have experience. How do they get the experience? And how do you get experience? Well, they've seen a lot of stuff. Well, you could see a lot of stuff too. You just have to approach it a little differently. You don't have 30 years to see the stuff. You have to compress it in a shorter time frame. And so you can do that. These are just recommended. One thing that surprised me when I transferred to UCLA was that some people do more. And you think, why? I would never do more homework than was assigned. Why do I want more work? And some people did, like this person that sat next to me I was talking to, and they did every single problem. They didn't literally do it. They just did what I was saying. They don't have time to do every single problem. They just read the problem, thought about how they do it, look at how the book did it, and then register that. They do it the same. That way they learn new tricks, new tricks being new ways to approach problems. That way, they were never surprised on the tests. They thought the tests were easy. That's why I talked to this person. They always thought, and whereas other people thought, oh, that test was so hard. It was nothing like they've ever, but this person was different. This person thought, oh, no big deal. This person was killing the class, basically. Yeah. So then I copied that, basically. So then I'll tell you, life became a lot easier after I started doing that, and it wasn't that time consuming to do. All right. So for Thursday, you want to finish these nomenclature, but these are going to be due, but we're moving on to chapter 13. So you want to start to chapter 13 because chapter 13 is 45 questions. This is very time consuming. One of my students kept a time log. And like, for example, chapter 16, he registered how many hours he spent on this. And it was like 40 hours. And I felt so bad because he had the approach that he needed to understand it, and if he didn't understand it, he wasn't going to cheat, quote unquote cheat. And so he's very against cheating. But, to me, it wasn't cheating. You just repetition is better, I think. So if you see it and then you can repeat it, that's great. A lot of people, they see it once and they can never repeat it. They'll see, okay, that's how you do it, and then they can't. It's like watching somebody play like an instrument, like a violin. Let's say you're not a violin player, but you watch somebody play the violin and go, oh, okay, that looks easy. But then you try to repeat it, you can't repeat it. So watching somebody do this who has 30 years of experience might look easy because they know what to do. They know which path to take. But if you don't know which path to take, then it can be hard. But anyway, I still have the book. I can get you the accurate answer if you want to see, get an idea. It's sitting in my office, kept it. But he complained that the homework load was too heavy. And I believe him.
40 hours is a lot.
40 hours is a lot for one chapter. All right, let's go back. See what we're doing today. Were there any other questions before we move on? This is not right. So we're done with chapter 24. Chapter 24 was just a quick hit, introduction to complexes. We're going to come back to chapter 24 and look at that more depth at the end, near the end of the semester. We're going to move on to chapter 13. Chapter 13 is thermodynamics part 2. Thermodynamics is a very tough subject. It's a tough subject because, things build on top of it. And so if you don't get a good foundation in thermodynamics, you're going to have a hard time. So, for example, tell me what the symbol is for total energy. U. Good. And what do we call U? Okay, you forgot. Okay, if you use the total energy, what does the total energy, what's it comprised of? Kinetic and potential energy. Good. And then what is it equal to? So if I have a change in total energy, that change in total energy is equal to?
Is it the work thing?
Yes. The work thing plus the?
Minus NR2.
No, not minus N. It's work thing plus the blank thing.
I forget what it's called, but it's negative P.
Yeah, that's the work thing.
That is the work thing.
Yeah. The work thing plus the? Enthalpy is a little bit different. Enthalpy, what's the difference between internal energy and enthalpy? What's the difference between internal energy and enthalpy? See, now you're already struggling in thermodynamics. That's typical. You're going to struggle in thermodynamics, and lots of people end up. The class I was talking to you about with the guy sitting next to me, that was thermodynamics, like upper division thermodynamics. That class has a huge failure rate that at UCLA, they print out bumper stickers like I passed Chem, which is thermodynamics. And so a lot of these are chem majors. A lot of these chem majors are failing out of thermodynamics. They're failing out of thermodynamics because they can't even tell you what U is exactly, and they can't even tell you what H is. And so they don't even know that, and then they're trying to go on, right? If you don't even know the basics, then how are you going to get the more advanced stuff, right? You're destined to fail. And so anyway, so this is thermodynamics part one. I mean, part two, do you have thermodynamics part one? And so what I was asking you about was the first law of thermodynamics. We have the first law of thermodynamics. Can you tell me what the first law of thermodynamics states?
Conservation of energy.
Yeah, conservation of energy. Energy is conserved. Conservation of energy means the total energy of the universe is fixed. Well, energy is fixed. In other words, energy is neither created nor destroyed, right? Energy is neither created nor destroyed. Neither E. Okay, I can't remember. Created nor destroyed. And these ones here have to be modified a little bit. That's because we have this relationship between energy and mass. And so there could be mass energy conversion. That is, some energy can be destroyed and converted into mass, or some mass can be destroyed and converted into energy. And so in Chem 4, they modified this to energy and mass are conserved, and they're related. However, in this is only significant in nuclear reactions. In chemical reactions, the mass changes and the energy changes, these conversions are very small, that they're difficult to measure. So how do we express this in terms of equations? If the total energy of the universe, total energy is fixed in the universe, then how are we going to see energy changes? How can there be energy changes if the total energy doesn't change? And the way there can be energy changes is we have a system and a surroundings. The systems plus the surroundings equals what? The universe. So we could look at delta U of the system. Delta U of the system will be equal to minus delta U of the surrounding. This is total energy here. Now, when we look at the system is equal to Q of the system plus W of the system. Does this look familiar? This is going to equal Q minus Q of the surroundings plus W of the surroundings. And so we have one application. Let's say the work were zero. If the work were zero, then the first law simplifies into this. Q of the system. What was Q again called?
The heat release.
The heat. Yeah. Q of the system, it could be released or it could be absorbed. It's equal to minus Q of the surrounding. So this would be the first law of thermodynamics. Yeah. Or we could have this. This would be the first law of thermodynamics here as well. First law. Etc.
Okay, so just to be sure, Q is heat, W is work, and U is
Use internal energy.
internal energy.
Use internal energy, which is equal to what? E sub k. Petrucci likes this symbol for E sub k. I use capital E, capital K, but it doesn't really matter. What does it represent? Kinetic energy. And I'll just use PE for potential energy. Internal energy of something, or the total energy of something, is equal to its kinetic energy and potential energy. So what is the energy of this table? The energy of this table right now is its kinetic energy. It's kinetic energy because the atoms are vibrating in the table. It's not freezing cold. And it's potential energy. So this table, it's the potential energy to do what? Potential energy for chemical reactions. So can I burn this table? Will it burn? Will this table decompose if I heat it? Lots of different things we think about. In fact, decomposition with heating is such a big problem that we want to minimize the amount of heat we give certain things. So we have specialized equipment to try to do that. Things like vacuum ovens. Vacuum ovens, you can dry things at much lower temperature. Our ovens here are set at 112 degrees, the drying ovens. Did we use drying oven in 1A? Yeah. Did you guys use a drying oven in 1A? It's about 112 to 120 degrees. But for some compounds, that's too hot, like drugs or something else. You don't want to, but we want to dry them. So how do you dry them? Well, you put a vacuum pump on it, and it helps suck the water out. Lowers the boiling point of water. Well, anyway, kinetic energy is just the average temperature. The average kinetic energy is related to temperature. Potential energy is potential to react or cool down or heat up, relative to other things. Delta U is the change in internal energy. That's equal to the change in kinetic energy plus the change in potential energy. And that change is going to manifest. So if we're losing energy, it could be that we're losing energy in heat and or work. So we can lose energy in the form of heat and or work to the surroundings. So we could have an exchange. Or we could be going lower in potential energy. Going lower in potential energy is going downhill. You're going from less stable reactants to more stable products. That kind of stuff. Or we could be going up in energy. That kind of thing. So you want to review some stuff from this chapter, like H. What was H? H is equal to internal energy, right? And what? It's kind of related to work. It's H is equal to U plus the pressure volume state. And so if we have delta H is delta U plus P delta V.
And then isn't that also equal to negative change of M RT?
Which one? P delta V?
Yeah.
Negative what?
NRT.
nRT.
If PV equals NRT.
PV equals nRT. Usually it's P delta V is equal to
Delta NRT. Or negative.
P. There could be different things. So, for example, you could hold N constant, or you could change N. That's going to change the volume. R is a constant, or you could hold the temperature constant, or change it. And so, or both. We change both the number of moles and the temperature. That's going to lead to volume change. And so, it's not one fixed thing. It depends on what we do. So rather than doing this, we just look at what, regardless, how did the volume change? Rather than come up with a specific, because the volume can change in different ways. But what the point is why do we have this extra factor PV here? Does anybody recall?
Because there's like so many different types of work.
Yeah.
So we limit it to pressure volume. And then that way we can, I don't know the exacts, but then we need to limit it.
Right. Normally when we look at the internal energy, we're just looking at the internal energy of one thing. And so we're looking at the change in the internal energy of this. Let's say we're looking at the change in internal energy of something like this, where we have U initial. U initial is going to be methane plus 2 oxygens, gas. And then let's keep the temperature at 25 degrees C. Although when we combust this, it's going to get very hot. But initially, we'll just say the temperature is 25 degrees C. And what does this form?
Carbon dioxide.
Yeah, this is going to form carbon dioxide and actually 2 carbons. This is going to have lower energy. But what we're going to do is we're going to let the carbon dioxide and water cool back down to 25 degrees C. So we're going to do this reaction, room temperature. The temperature is going to skyrocket and then cool down again. And so the change here is going to be delta U is equal to delta EK plus delta PE. Did the kinetic energy change here? So we start at 25 degrees C and we end at 25 degrees C. Did the kinetic energy change?
No.
No. But the potential energy changed because methane and oxygen is an unstable, explosive mixture. If this room filled up with methane, you better be worried, because if somebody has a spark or ignition source, it could just be a hot surface, then it could potentially explode. And so methane and oxygen is a potentially explosive mixture. CO2 and water, you could have a little explosion like carbonated beverage explosion, but it's nothing like a methane explosion, right? And so CO2 and water is going to be much safer, much more stable. But internal energy doesn't tell us what's going on with the surroundings. Our system is the combustion of methane, and that's what we're looking at here, the combustion of methane. But during this combustion of methane, what's happening to the surroundings? Well, you think nothing's happening to the surroundings. The surroundings are going to get warm, for sure, because the drop in energy has got to go to the surroundings. But other things can happen as well. It depends on if you do this. And in thermodynamics, we have 2 universes. We have the constant volume universe, and we have the constant pressure universe. And so we got to look at what universe we're dealing with. Are we in the constant volume? If we're dealing in constant volume, then we have to work with thermodynamics of constant volume systems. And we can't apply all equations. So, for example, if we're dealing with constant volume, then our delta H calculation may or may not be correct. Because delta H, one of the assumptions that you make in using delta H is that you're not in the constant volume universe. You must be in the constant pressure universe. So if you're using delta H in the constant volume universe, you can only use it in special cases where it doesn't matter which universe you're in, you're going to get the same answer. Do you guys know that? And so let's say you're taking a test. On the test, one of the conditions is this constant volume, and you're doing delta H, and you're getting the wrong answer. But you're plugging in the right numbers, or you think you're plugging in the right numbers, right? And so it makes it hard. Well, even the ideal gas law can be hard, because let's say you're using the ideal gas law and the pressure were 10,000 bar or 10,000 atmospheres. Are you going to expect to get a decent answer? No. I mean, you might get an okay answer, but it's probably going to be way, way off. And so the same thing happens here. You know, one of the, when we derive H, the origin of H is equal to what? What is the definition of H?
Which is enthalpy. Which is
H is,
minus
yeah,
MC
enthalpy.
delta
What is
T.
the definition of enthalpy? Which is equal to H. H and enthalpy are the same thing.
Yeah.
So what is the definition of enthalpy?
Isn't it negative MC delta T?
Q is equal to MC delta T. Q's. But this is not, this is only if you have an object that heats up and cools down. Or Q is equal to amount times delta H. Or that's for the constant pressure universe. This is what we call Q sub P. Then we have something called Q sub V, which is the amount. If you want an equation that always works, it's the amount times delta U. Sometimes QV and QP are the same thing. Tell me when QV and QP are the same. Now, if we restrict it to only pressure volume work, then H is defined as QP with the restriction that the work is PV work only. Does this all sound familiar? So if you're taking thermo, then you want to make sure you have the basic, definitions and all this stuff down, the equations. You want to make sure you're using the right equation for the right universe. It's like those science fiction worlds. Some universes operate by different rules. It's like different countries traveling to different countries. You have to look at the norms of that particular country. But anyway, getting back to this, then all this stuff is good stuff to review, so you understand. And if you're continuing, you might think, I'm not going to continue with this thermodynamic stuff, but you might be surprised they have thermodynamics for engineers, which might be even more miserable than thermodynamics for chemists. They have thermodynamics for biologists. The thermodynamics for biologists, I heard, is less miserable than the thermodynamics for chemists. So, but they, in biology, energy is such an important thing. Right? And they have biological standard conditions as well. But et cetera, et cetera. This is all this stuff. And so review some stuff. It would be good. It's easy to forget this stuff. Or what I had to do when I was taking it was I had to go buy their book. So I bought normally I'd look at the books that are a step above. In this case, I had to look at the book that was below because I had so many holes in my understanding. Didn't understand much. In thermodynamics, they say you still don't understand. It's just too hard to understand. But anyway, this is all first law stuff. Energy is conserved. So we're looking at exchanges of energy between the system and the surroundings, and the forms of exchange. It's just exchange in the form of heat and or work. That's it. And we have different kinds of work as well. We have, tell me the different kinds of work that can be done.
times distance.
Okay, force times distance, that would be more mechanical work. And so we could do mechanical work. Or it could be volume, pressure volume work as well. You know, expanding volume, contracting volume. But getting back to this, the difference between internal energy, which is the total energy, and enthalpy is they're the same thing. Enthalpy is the total energy, but we add one additional state, and that's the pressure volume state. The pressure volume state is going to tell us how it interacts with the surroundings. So when we look at the combustion of methane, do you know a mole of gas, a mole of methane at room temperature and about 1 atmosphere or 1 bar occupies how much volume? About 25 liters. And so this is about 25 liters. 2 moles of gas here, 2 moles of oxygen is about 50 liters. So altogether we have a 75 liters worth of gas here. So we go from 75 liters to 1 mole of gas. 1 mole of CO2 is going to be about 25 liters, and then 2 moles of liquid water. How much volume is 2 moles of liquid water? Well, 2 moles of liquid water weighs 36 grams. 36 grams is going to occupy what volume? 36 grams of liquid water occupies 36 milliliters. And so we're going to go from about 75 liters to about 25 liters. There's a huge volume change. The system saw a huge volume change. So you go, so what? So what? That's going to have an impact on the surroundings. So if the system loses about 50 liters of volume, then that means the surroundings must have grown by 50 liters. If the surroundings grows by 50 liters, then that means the surroundings had to do work. If the surroundings had to do work, then there was energy involved. If there's energy involved, then we have to calculate that energy. And so this is what enthalpy does. We need the PV state in order to calculate the energy exchange between the system and the surroundings due to volume changes in the system and the surroundings. So this is, and sometimes what happens is the surroundings gives the system more energy. Sometimes the surroundings takes energy away from the system, and sometimes there's no change. There's no exchange. And so maybe you can review some of that. You know, some of this stuff we aren't really going to have to review for this. All right, so that's kind of the first law. And do you know how many laws of thermodynamics there are? There are 3 laws. And so in this chapter, we're going to look at the second law and the third law of thermodynamics. And so let me just talk about the second law. I got to delete a bunch of stuff. Probably these recordings. Didn't have too much disk space. All right, so we talked about the first law, and it's good to review all that stuff related to the first law. Now we're going to talk about the second law, and we're going to get some more symbols. Thermodynamics loves symbols. We're going to get 2 new symbols for the second law. The 2 new symbols are S and G. S, do you know what this is called? Entropy. Entropy is a measure of disorder. So the higher the S, the higher the disorder of the system. That's one way to think about it. That's called positional entropy. G is called the Gibbs free energy. Gibbs free energy. And we have the third law of thermodynamics. I'm going to talk about the third law first. I'm going to go kind of out of order from the book. Third law is pretty simple to remember. Third law deals with S, the entropy. And all the third law says is that the entropy of a perfect crystal at 0 Kelvin is 0. The entropy of a perfect crystal at 0 Kelvin is 0. You know what this does? This gives us an absolute 0 of entropy. In thermodynamics, we don't have absolute zeros. Think back. What is the absolute 0 of internal energy? Or so, for example, if I wanted to calculate or I wanted to measure the internal energy of this table and get the absolute internal energy of this table, what is it? Or maybe not this table, let's say a glass of water. If I want to know the absolute internal energy of a glass of water, what I have to do is I have to break it apart, right, and then put it back together. If I break it apart, first thing I'll probably do is break the hydrogen bonds and the dispersion forces that hold the water molecules together. So breaking bonds, does that cost energy or does that release energy? So if I want to break let's say I want to boil the water, does boiling the water cost energy or release energy? It costs energy. So what we say is that there's internal energy stored in the hydrogen bonds. The internal energy is holding the water molecules together. So energy is conserved. So if I have to input energy to boil the water, okay, to condense the water, what happens then? So I reverse the process and I condense the water, what's going to happen? Energy is released, since energy is neither great. So in one direction, it costs you energy, and the opposite, it releases the same exact amount of energy. And so the energy is stored in the hydrogen bonds. Okay, the next thing I'm going to do is I'm going to break the covalent bonds holding the oxygens and the hydrogens together. So I break those covalent bonds. That costs energy. So to make the bond, it's going to release energy. So this is what we say, energy stored in the bonds, bond enthalpies. And then I'm going to pull all the electrons off the atoms. If I pull all the electrons off the atoms, that costs energy too. So there's energy potential. We call this potential energy. There's potential energy in the electrons holding onto the nucleus. Okay, so once I remove all the electrons, it's going to cost me energy, that potential energy. Then I am left with a nucleus, but inside the nucleus, there are, protons and neutrons. So I tear that apart. That's going to cost energy. So when do I get to the bottom of this? I think particle physicists think they pretty much have it sorted out. They get to the bottom when we're at quarks. Everything's made up of quarks. So once we get to the quarks, but then, then they're talking, okay, a proton's made up of 2 up quarks, 1 down quark, or something like that, and this and that. But I just watched this other video, and they're saying, well, they're getting some weird things, like there are charm quarks inside, and charm quarks actually way more than the proton itself. So how could there be a charm quark? And they're talking about, well, the energy, there's massive energy when they were breaking it apart. So maybe that's what created the charm quark, which is what they're observing. But is it going to be easy to get to absolute 0? No. And do you think, it's going to reach the bottom, it's going to be tough. And the same thing happens. We see this happen here. Let me show you. I'll just show you a simple example, and then we'll go back and we'll look at another example that we saw. Did I close it? I might have closed it, unfortunately. Yeah, I was thinking I'll need it, but then I closed it. And what I wanted to do is go here. I want the absolute zero of oxidizers. I want the absolute zero of oxidizers. So, for example, lithium ion, is that the absolute worst oxidizer in the universe? If this is the absolute worst oxidizer in the universe, then I'm going to call this zero. The strength of lithium is zero because it's the absolute worst oxidizer in the universe. And then I have an absolute scale. Everything else is going to be better than lithium ion, right? But somebody discovered a worse oxidizer than lithium. Do you know lithium metal? Lithium metal is much worse oxidizer. So maybe we should get lithium metal to zero. And so a lot of people want to write lithium metal on this side. You could. It'd just be way worse than lithium ion. It'd probably be down here. Maybe that's the absolute worst oxidizer in the universe. Would you think so? Are you confident to say that lithium metal would be the absolute worst? And then somebody will say, maybe not lithium metal. Maybe fluoride would be even worse than lithium. Fluoride doesn't want another electron because it has to go in the next shell. Fluoride fills the second shell, and the extra electron would have to go in the third shell, which would be a lot higher in energy. And so, do you think it's easy to find the absolute worst? And so, you know what people do? They say, forget it. I'm not going to find it. Let's say you're trying to find the absolute coldest temperature, and you go, okay, I want to call the absolute coldest temperature zero. But, things got colder and colder, and you didn't know where it ended. And so you might say, screw it, I'm just going to name something zero. We're just going to call that zero, and then if there's stronger, that's fine. If there's weaker, that's fine. That's called an arbitrary zero, right? And so what somebody did was, okay, what's a common oxidizer? Very common oxidizer in the laboratory. Every laboratory has this very common oxidizer. Oxygen, but oxygen's a hassle. You can't put it in a bottle easily and work with it. So let's say I wanted to make a 1 molar oxygen mixture in the air and test that against a 10 molar mixture. It's more pain to work with gases. But oxygen's a great oxidizer and it's free. Unfortunately, this oxidizer we have to pay for, but in every lab has it, and under standard conditions, which would be 1 molar. You guys remember standard thermodynamic conditions. Did I mention that? I think I asked that before, right? Yeah. So let me talk about that here just briefly. So we have delta U and we have delta U standard. And we have delta H and we have delta H standard. So we need to know that difference. So this chart that we're looking at here do you see this, what it says here, standard? That means it's under standard thermodynamic conditions. That means that H plus is at a concentration of what? 1 molar. So what lab? Well, it might not have 1 molar, but all these would be at 1 molar. So we could pick one of these, like lead 2. And does every lab have lead 2, 1 molar available? Yeah. So looking at these, probably the greatest availability for oxidizer would probably be what? H plus, because you might have 6 molar H plus. Well, you just do solution dilution. You'll get 1 molar easily, right? So H plus is easy. And so what they did was they just said an arbitrary zero. Do you see the zero? That's not an absolute zero, that's an arbitrary zero. And that zero is just chosen. H plus is convenient. Every lab has it, and so why not just pick that as the zero? And so that doesn't mean it's the worst oxidizer in the universe. It means that, that's H plus, and we're going to have oxidizers that are worse. This one, lithium ion, is -3 worse. And then we're going to have oxidizers that are stronger. And the oxidizers are stronger would be fluorine. Fluorine is close to +3 stronger. And those units for this are volts, +3 volts stronger of an oxidizer. So this is arbitrary 0. And we saw this in Appendix D. Do you guys remember in Appendix D there were some zeros, delta H of formation? Why is the delta H of formation 0? For this. Let's see. Well, anyway, the point is, I'm just kind of rambling on with this, but the point is just maybe do some review, and then just try to pick it up. And easier not to cram everything the night before the test. That's what kills people in thermodynamics. But like delta H of formation of H plus is equal to 0. But why is that? Because a formation reaction would be 1/2 mole of H2 gas. This goes to H plus aqueous. And the delta H for this reaction is 0. How can the delta H of this reaction be 0? We have to break 1/2 mole worth of bond. We have to ionize it. Breaking 1/2 mole of hydrogen bonds is going to cost you hundreds of kilojoules. Ionizing it's going to cost you. Ionizing hydrogen is very difficult because of its small size. It's going to cost you over 1,000 kilojoules to ionize. How's this 0? Well, forming the solvated H plus is going to be favorable. Why is this 0? Because it was defined as 0. It's not 0. It's just defined as 0. How can they define it as 0? Isn't that going to screw everything up? Well, no, it's not going to screw everything up because it leads to a systematic error which gets canceled when you look at the anion. Do you guys remember this? A little bit? Probably a little bit. And so repetition helps. But if you're planning to go on to thermo, you got to know this stuff. Otherwise, you're not going to be able to do calculations. So, and it would be great to do it the first time round rather than the second round. I was thinking I have to do a second round, but fortunately made it to the first round. Anyway, let's go to the second law. So, the second law talks about driving force. Some people don't like this term, driving force. But I'm going to use it. Driving force is what we call spontaneous. If there's a driving force, then it should happen spontaneously. Things without driving force can happen, but you have to force them to happen. They don't just happen spontaneously. So a ball rolls down the hill, but the ball can roll up the hill, but you just got to push it along, right? And so we're going to look at this. And so from observations, I should have saved it. Yeah. Good. Let's save this. So we already talked about driving forces. Driving forces are going from less stable to more stable. And if we're having that, less stable to more stable, we expect the reaction to occur. But when we look at driving forces, there are different degrees of driving force. So let's look at the percent reaction. If there's absolutely no driving force, then we expect 0% reaction. And if we have driving force, then we expect 100% reaction. And so this is how we're doing our predictions. If a precipitate forms, we expect 100% reaction. If no in metathesis, if a precipitate forms in redox, you don't know. It may or may not happen. But anyway, going back to this, it's kind of black and white. But it's good to know because we want to know, do we expect a reaction or don't we? But what we see is that there's going to be a whole range of values in here. And so what we want to do is we want to quantitate it. It depends on how far downhill are you going. If you're just going down just a barely like a driveway, is that much of a downhill? No. But if you're going down a steep mountain, that's a huge downhill. And so we might have a driving force, but it could be fairly weak. And not only, if you go down a driveway, is it hard to reverse and go back up that driveway? If you have a little, no, it's not hard. You can go back and reverse. And so in Chem 1B, we need to know this quantitatively because the more quantitative we are, the better. But in order to get this quantitative, we first want to have a good grasp of it qualitatively. And so in Chem 1B, what we're going to do is we're going to do Chem 1B style stoichiometry. So in Chem 1A stoichiometry, it's either 0 reaction or 100% reaction. In Chem 1B stoichiometry, it could be like 98% reaction or 1% reaction or 50% reaction, And so in Chem 1B, we want to predict, how much. So I gave you some examples. I said, there's greater than 99.9%. Well, how did I know there's greater than 99.9%? Did I calculate it or did I measure it? There are two approaches that we can take. And so this will be Chem 1B stoichiometry. In order to do Chem 1B stoichiometry, we need to know how much reaction takes place. Therefore, we need to know this driving force, or we need to know this, spontaneity in detail. And so qualitatively, when we look at driving force, let's go qualitative. Nature tends to do two things. In nature, spontaneous things happen when we go down in energy. So we want to lower energy. That's spontaneous. But also, we'd like to increase entropy. Now, what we have to do is it's going to be a combination of these things. It is possible to go up in energy. How do we go up in energy? So, for example, if you have a cold pack, like they have these ones where you break the packet inside and it gets really cold. Is that an endothermic reaction or exothermic reaction that's occurring there in the cold pack itself? It's an endothermic reaction. It's an endothermic reaction. So in a cold pack, what's happening is we're at higher potential energy. We break it, and then we drop down to lower potential energy. And then the surroundings is going to lose heat from the surroundings. And so it's going to feel cold. Does that make sense? So we're going down in energy. But have you seen those heat packs? The heat packs, when you break it, it gets hot. So if it's getting hot, it's got to be the reverse process of this. It's a different set of chemicals. And the reaction is not endothermic. The reaction is actually exothermic. Actually, I have this backwards, sorry. Let's fix this. Let me go back to cold pack. Endothermic reaction means it absorbs heat. And so we're going up in energy. And so the energy increases. In a heat pack, we're going down in energy. And so energy is going to be released. Yeah. Like this in the heat pack. So this makes sense because we're going energy is going down. So heat pack makes sense because we're going from less stable to more stable. But the cold pack doesn't make sense. How can this happen spontaneously? It happens spontaneously because you just break it. And once you break the internal barrier, it's not like you're shaking it or you're doing anything. It just spontaneously happens. There's a chemical reaction in there, and it sucks heat out from the surroundings. You're the surroundings. And so how can this happen spontaneously? The cold pack. Hot pack, yeah, that's fine. How can it happen spontaneously is this. This up in energy has to be compensated for by a large increase in entropy. So overall, this is unfavorable, right? So this is favorable. This is unfavorable. So the favorable part has to cancel out the unfavorable part. Yeah. And then it can happen spontaneously. So the favorable is greater than the unfavorable. Well, if that's the case, then what we need to do is we need to quantitate it. We need to know how much energy is involved. Well, this is chapter whatever, Chem 1A. Okay, so we can quantitate it. We can quantitate it in terms of delta H or delta U. Delta H if we're in the constant pressure universe, delta U if we're in the constant volume universe. This is going to be Chem 1B. Now we want to quantitate the entropy. And then we want to figure out how these balance each other out. This combination of energy and entropy is the Gibbs-free energy. The Gibbs-free energy is going to combine these. And so we're looking at energy and entropy. And we weigh them, are they weighed equally? Yeah, they're weighed. Like, for example, let's say the energy were positive 100 kilojoules. Well, positive 100 kilojoules means we're going uphill 100 kilojoules. Well, that must mean the entropy's got to exceed that, right? And so we got to make sure that entropy can compensate. And so it's energy and entropy terms. And this is the Gibbs-free energy is going to allow us to quantitate it. Well, in order to quantitate the driving force, we first have to talk about the entropy, right? And so we need to place numbers on the entropy. So we want to calculate the entropy changes just like we calculate the energy changes that we did in Chem 1A. Fortunately, entropy calculations are easier than, for the most part, at least the ones that we do are easier. And so the first thing is we have it. And so if you recall in Chem 1A, can we do this? Delta U is equal to U final minus U initial. Is this accurate? People do this calculation, but they get inaccurate answers. They get inaccurate answers because in order to calculate what we call the absolute internal energies, we can't measure those. And if we try to calculate them, we're going to make an assumption of where the bottom is. If we try to calculate it, it would be like making an assumption, what's the weakest or the strongest, oxidizer in the universe? What's the strongest? Do you know what the strongest oxidizer in the universe is? So absolute internal energies are not determined. So we got to figure out other ways to get delta U. Are there other ways to get delta U? Yeah, that's what thermodynamics is all about, is figuring out other ways to get delta U. What's another way to get delta U?
Find the changing kinetic, right?
Yeah, we can find the changing kinetic. So there are other ways. So if we can't do it this way, we can do delta EK plus delta PE, or we can do Q plus W, etc. Same thing goes with delta H. Delta H is equal to H final minus H initial. Do we determine that? No, the same problem is going to happen because H, as you recall, is U plus PV. And so we're going to run into the same problem. So this is never determined, not determined. But S is different. Delta S is S final minus S initial. So all we need is the final entropy minus the initial entropy. Why can we do this? Why can we do this now, but we couldn't do this before? Yeah, we have the absolute zero. We have the third law of thermodynamics. We know what the absolute zero is. The absolute zero is a perfect crystal. A perfect crystal means every ion, every atom is in the right place. There are no defects. And it's absolute zero. Absolute zero means everything's frozen perfectly. So you have it perfect, everything's aligned perfectly, and you freeze it. And that means that it's absolutely perfect. Well, if it's absolutely perfect, how many different ways are there of arranging a perfect system? It turns out there's only one way. Once you get it to perfection, then you stop, because can you have better than perfection? You can have worse than perfection, but you aren't going to have better than perfection, right? And so it stops there. And so this is a perfect crystal. And that means there's only one way of arranging stuff. And if you try to rearrange it, then it's no longer going to be perfect. So, one way. What happens if you start warming it up? If you start warming it up, you're going to start having vibrations. And those vibrations are going to result in multiple positions for the atoms. When there are multiple positions and you freeze it, then there are different ways you can arrange these. And so as the temperature gets hotter, the entropy increases. The entropy increases because there are more ways to arrange things. Or in other words, we can think in terms of degrees of freedom, how restricted is the system. The fewer the restrictions, the more ways, the higher the entropy. And so we'll talk more about this next time. But this is good stuff to review, so this add to your list of stuff to review. Okay, so we're out of time, so let's stop here.